about.
Exactly.
What's
Yeah.
the technology that you think is missing now or would be helpful to advance the research further? Question for both of you. Mike, maybe you can go first.
Okay, well, I think the biggest thing that's missing, there's a few things, but one of the biggest things that's missing now is the physiomics data sets. So we have these massive, I mean, just think about trying to do molecular biology before we had genomic data and transcriptomic data and all this stuff. What we still don't know is if you wanted to know in some model system, some organ under some disease state or at some stage of development, what is the bioelectric pattern? We only have like a tiny number of these things mapped out. And I mean, you know, Rich has done a ton of it with the vibrating probe. We've done some with the voltage dyes. But in the grand scheme of things, there's very little bulk data available. And that's pretty critical because, you know, modern tools like AI and other techniques require a lot of data to really extract the signatures and functional target endpoints and so on. So that's one of the things that we're focused on now, is trying to develop technologies where in some sort of high throughput way, we can actually generate these data sets so that we actually know what the native states are for these things. What do you think, Rich?
Yeah, no, I think you're absolutely right. I remember that beautiful paper that you guys came out with when you labeled the frog embryo with the dye that measured membrane potential in the different regions of the embryo and showed that actually got a picture, a visual picture of the gradient of potential in the blastomere stage of the frog embryo. And that is what we need. We need to have a visualization of the electrical properties that we're seeing. And it's so hard to do because the organisms that we want to study are multicellular, thousands and thousands of cells, but those cells are working together in a very intricate way. The ideal would be to be able to image the field, the whole electric field everywhere in that organism, and that would be a dream. It's not obvious to me how to do that, but I'm sure that one day we will have some molecules that will show the gradient in a way that we can image them. And I mean, there's quite a few different tools that are working towards that. This whole optogenetics business where you control gene activity with light. Be nice to be able to reverse that and show have light come out with the bioelectric activity. That would be fantastic. I hope that happens someday. I don't see it on the horizon yet, but I wouldn't be surprised.
Well, we've so we and others have now are generating transgenic mice where every cell is expressing one of these optogenetic voltage reporter proteins.
Okay.
So I think I think in the next couple of years we're going to have model systems where every cell is advertising its electric state, and then we'll be able to start.
There
I mean,
you go.
again, you still have the issue of you know, it's hard to see through tissue, right? And so what's
Yes.
going on? I mean, you still have all that, but at least the
Yes.
cells will be sort of, you know, trying to tell you what their voltage is as much as you can see them.
Exactly. That would be fabulous if we can get that to work. I love it.
Now, maybe this is a stupid question, but do different humans have different electrical states around the cells?
Different humans.
As in you and me and Mike, are our electrical states around tissues and organs and cells going to be different, or do all cells, like normal cells, have the same type?
I think it would be generally be the same. I guess it depends on the disease state. So clearly, if I would say that as you get older, I know for a fact that the patterns and the voltages get lower. So I've shown that in a skin wound, for example, as you age, the amount of current flowing, the wound current, goes down. You just don't have quite as much energy, so to speak, to drive the current. So I think you would find a difference as a function of age and any kind of disease state, for sure. In general, a healthy individual will have very similar patterns than than not. It really depends on what you're looking at, but typically you'll find a voltage across every epithelium, every organ, and that voltage will drive currents in depending on what that organ is doing. Yeah.
I mean, there's also there have been stories in the cancer field about sodium versus potassium rich diets, and
Yes.
this, right, and so one can hypothesize that if what we're talking about is this kind of like a change in resting potential due to sodium and so on, you might expect, right, people with different diets to actually have shifted VMEMs that would predispose you to different different conditions like cancer and so on.
Absolutely. I mean, it's been shown pretty well that depolarization is required for a cancer cell to be very active. They're typically, when you look at their membrane potential, they're more depolarized than a healthy cell. So that obviously you want to avoid